Hello friends, my name is host Eric. I'm the host of Talking with Famous People, and I would like to talk to you today about three different kinds of reasoning problems or questions and what they kind of reveal about a variety of different things. So, one example of a reasoning question that you're probably familiar with is one where a category error creates a paradox. And a simple example of that is if a tree falls in the forest and no one's around to hear it make a sound, it doesn't make a sound. And the answer is, well, if a tree falls in the forest is something that is implicitly saying if it is observed that a tree falls in the forest, whereas the second premise says it is not observed. So that's where the paradox comes from, is in the category error that suggests that you can have an instance of a category of thing called unobserved behavior that is observed. The envelopes problem is a rather famous probability reasoning problem that exploits this same kind of conflicting premise in order to create a apparent paradox. And the envelopes problem goes like this. There are two envelopes, A and B. A and B both have money in them. A is either 10 times or 1/10 of B. In other words, one has 10 times as much money in it as the other. And the likelihoods of the amounts in each of the envelopes goes down as the amounts go up. Infinitely closer to 0% chance as dollar amounts go up. So it's either $1 or $10, 10 or $100, 100 or $1,000, 1,000 or $10,000. Those are the possibilities in terms of the two envelopes, right? And there's a 50% chance that it's $1 and $10, a 25% chance that it's $10 and $100, a 12.5% chance that it's $100 and $1,000, etc. So let's say you have these two envelopes, A and B. A and B. And you are told, okay, pick an envelope. You can't tell what's in it by how fat it is, okay? And you pick A. And then you're given a chance to look at it. And you look at it, and you see how much money's in it. Let's say it's $10. Should you switch? Okay? That's the question. It's basically, should you switch? After you look at it. And what's interesting is if you do a normal sort of probability calculus on this, you determine that yes, you should switch. Definitely every time after you look at it, no matter what it is. Now, if instead you look at the other one, then in all cases, you should not switch. So it's not clear what the probability is telling us here. Wait, should I switch or should I not switch? If you look at it from yet a third perspective, it'll appear that it's a null set. That it's like it's exactly the same. Whether you should switch or not switch, but the reason it gets there is because it says you should switch under these conditions and you should not switch under these conditions, and it depends on which one you look at, right? But that shouldn't impact whether or not you should switch or not, right? Well, which one you look at, because presumably the things are neutral. There's an equal chance for the one that you look at to be the lower or the higher number. So the thing is, the barrier here in terms of understanding, well, let me just point out this. There's one clear instance in which you always switch, and that's if you see a $1, right? Because you know the other one has to have more. However, it turns out that the same, even if you don't know that for sure, the other one has to have more, that the amount likely there's always a net profit if you measure the difference when you choose the other one given the percentages. Which is to say, if this is 10, the chance is this one might be 100, or the chances this one might be 1. So if I pick the other one, I could get a $90 profit, or I could lose $9, and that mechanics will always be in place. Yet it doesn't seem to make sense that you should switch the envelopes. Well, the problem here is that the probability measurements are missing the necessary third leg, and the paradox is resolved by operationalizing your definitions. If you say, my goal is to not lose more than $500. In other words, I don't want to make a choice where I regret it a lot. I'm trying to minimize my amount of regret. Then all of a sudden you can make a determination about the thing. Regardless, you can't get this general rule because of the fact that there needs to be some third leg that's stable. The problem with this, of course, is it goes infinitely closer to zero. So there's no stability in the finiteness of that set. So in order to get stability in the predicted model, you have to have the finiteness come out from something else, which is defining the person's relationship to it, which is kind of like the tree falling in the forest. You can't you can't even potentiate an answer without a certain amount of points, right? You can't draw a line without at least 2 points. So that's what the problem is with these things. It's basically it's giving you 1, not 2, or the second one 2, not 3 that it needs, and then trying to make conclusions that it can't make from it. All right, now let's look at example set 2 and see how that differs. Example 2, data and set relations test. So the thing is, when we look at 2 and 3, they break down to the same kind of problem sort of at the end, but they start off with different situations. This mechanical horses problem is a problem that Google gives potential employees, apparently, or a problem that companies like Google sometimes give employees. Well, probably not anymore now that it's famous. But it posits that 25 mechanical horses, each traveling a mechanical horse track at a predetermined rate. So if we call the horses A through Y, A, every time it goes around the track, goes the same amount of time it takes to go around the track. So let's say it's 1 minute. It'll go around the track. Every time it goes around, it'll go exactly 1 minute, okay? No two horses have exactly the same speed, so every horse has a different finishing time, either more or less than, let's say, a minute. And you can race 5 horses at a time. What's the minimum number of horses to determine the 3 fastest horses? So when I was first asked this question by a person, they didn't specify all the stuff that was necessary, and I'm like, well, it's really hard to say because the horses are going to get tired. Well, these mechanical horses don't get tired, okay? You can race 5 horses at a time. What's the minimum number of races to determine the 3 fastest horses? So the first pitfall in this question is that to note that when you're sort of gathering data, that you run horses A, B, C, D, E in one race, F, G, H, I, J in another race, K, L, M, N, O in another race, P, Q, R, S, T in another race, U, B, W, X, Y in the last race, right? And then you're going to take the winner of each of those sets. So let's say it's the first letter in each of those sets that go up against each other in the 6th race. So then you've got, well, I mean, let's change it around so that it's set A, number 1, set B, number 6, etc. That makes it easier. So you have, let's say B1, I mean A1, B6, C11, D16, and E21 have won their respective races. So you know you're going to put those 5 against each other. And then the winner of that is going to be the fastest horse. But you don't necessarily know that the second and third place of that are faster than, say, the second place horse that the winning horse was racing against and beat. So let's say the fastest horse is A1, wins the winner's race. Well, you don't necessarily know that A2, who didn't get into the winner's race, isn't faster than B1, C1, D1, E1, right? So in order to figure this out, you first have to recognize that simply running a 6th race and going, well, I'll go 1, 2, 3 in the 6th race, and those are my 3 fastest horses, that won't produce your 3 fastest horses necessarily. So it's recognizing that's your first pitfall. And then the solution is to eliminate those horses that cannot be among the fastest 3. You could start with anybody below the 3rd place of the winner's race. Like, in other words, if say it goes set A, set B, set C, set D, set E winners in that order in the winner's race, then set C's 2nd place can't possibly be the 3rd fastest horse, right? And anyway, there's you could eliminate all the ones that can't be, and you end up with 5 horses because you can eliminate the winner of the winner's race as well, because we already know he's the fastest. And then you take the second and third place horses, the first and second place horses from that 7th race, and make them into the second and third place fastest horses overall. Okay, so that breaks down into a process of elimination question, but it starts out as a question that it's about whether or not you recognize what data can be gleaned from sets, which is kind of conditional determinist, like what can you determine from certain conditions, right? But it's more conditionality than it is ordinality. Example 3, the hats problem, which I sometimes ask in typing questions. There are 5 hats in a bag, three red hats, 2 white hats. A person's wearing one of these hats cannot see his own hat. So if I have one, it's like a little party hat, right? There are 3 blindfolded prisoners. You each pick one randomly from the bag, and they're told if they can name their own hat color, they'll go free. If they name it wrong, they'll be killed. And if they don't know, they can choose not to answer. And then, in turn, their blindfolds are removed. The first guy, he looks at the other 2 guys. He can't tell his hat color. The second guy looks at the first guy and the third guy, and he can't tell his hat color. The third guy doesn't need to have his blindfold removed. He states what his hat's color is and goes free. So the question then asks, what color is this hat and why? So I'm going to go into the answer now. If you wanted to pause it there, to pause it now. Okay, I'm going to answer. So the thing is, the pitfall here is you've got to update your knowledge base. When you imagine the perspective of the first guy, you imagine him looking at the other 2 hats and try to figure out if he were able to tell the answer correctly, what would he see? And the answer would be he'd see 2 white hats. Then he'd know his own hat was red, for sure. Because there are only 2 white hats in the bag, and there are 3 red hats. So if the other 2 guys have the 2 white hats, he must not have it. It must be red. But then you have to update your knowledge base. When you get to the second guy, you've got to put yourself in his mind and say what he has learned from the first guy before doing his calculus. And if you don't, you have to follow that thinking process of each party from the spot where the last party left off, not from the problem's base. You don't return to the base with each party who's taking the blindfold off, and that's where you're sort of frame-walked by this question. And the solution is just a conditional elimination problem. So you can conclude that if the first guy had seen 2 white hats, he would have known his own hat was red. That the second guy knows if the first guy had seen 2 white hats. So the second guy knows if the third guy's got a white hat, his own hat must not be white and he must be red. But he's not able to say that, so then the third guy must know that his own hat is red. Delicious red. Wonderful red. I would also state that another problem that's not listed here that I want to mention briefly is the troll question. And when I was typing in INFJ the other day, she pointed out, and it's worth restating, the way that problem works is to frame walk the person into presuming that things that are described in the problem initially are necessary states of being, rather than things that, in other words, it basically positions stuff that's furniture as stuff that's beams of a house. By saying, every time food crosses the river, or the troll takes 10%, it sets it up as though that's the only way to get food across the river. It doesn't set it up as a problem that directs your attention towards the issue of how to feed the people, but rather how to prevent the thing that happens with the river crossing from happening. And so you end up focusing in too narrow of a frame and forget the larger picture, which is how to feed the people. If you've not heard the answer to the troll question or heard about it, I've talked about it extensively in other videos. Anyway, I thought that would be interesting to contrast these different problems. They're all forms of TI questions, really. But they explore different kinds of TI understandings. In other words, different relationships with extroverted intuition as well as introverted thinking. These kind of ones that are categorized as creating a paradox are trying to play on the frame walking thing in the same way that the troll problem is. And an extroverted intuition it typically provides the way out of that. It says, okay, let's challenge these fundamental frames that I'm assuming are fundamental and see if they really are. And so NE does play a role in solving some kind of deductive reasoning problems. In other words, it's not necessarily going to be the case that SETI is just as good at all of these kind of problems as NETI. especially something like the tree falls in the forest, where it's presenting a very NI concept and only breaks apart when you recognize what's implicit to the premises. That's probably something that's going to take an NE person, NE TI, to figure out rather than SETI. But I could be wrong about that. So anyway, thanks for watching. Hopefully you enjoyed this. I know I got a little dense there in the middle, especially about the horses problem. I got a little complicated in the explaining of it. But, you know, I did the best I could.